Albert Einstein's theory of relativity, comprising both the 1905 special theory of relativity and the 1915 general theory of relativity, revolutionized our understanding of space-time and the very structure of the universe. The special theory of relativity introduced the revolutionary concept that time and space are not absolute, but relative and intertwined into a single four-dimensional continuum known as spacetime. Before Einstein, Isaac Newton's system of absolute time and space reigned supreme. However, Einstein's equations showed that the measurements of time and space depend on the velocity of the observer relative to the object being observed. It has led to such mind-boggling consequences as time dilation, where moving clocks go slower than stationary ones, and length contraction, where objects shrink in the direction of motion as their speed approaches the speed of light. Einstein's general theory of relativity expanded these ideas to include gravity, which was reinterpreted not as a force acting at a distance, as Newton had described, but as the curvature of space-time under the action of mass and energy. Massive objects, such as stars and planets, create warps in the fabric of space-time, and these warps dictate the motion of objects and the passage of time. This concept was clearly confirmed during the solar eclipse of 1919, when observations showed that light from distant stars swirled around the Sun exactly as Einstein's equations predicted. The implications of the general theory of relativity were profound and far-reaching. It has allowed us to understand phenomena such as black holes, whose enormous gravitational fields bend space-time to the point where even light cannot escape. It also predicted gravitational waves, ripples in space-time caused by accelerating masses that were directly detected a century later in 2015 by the LIGO experiment. In addition, the general theory of relativity is essential to understanding the cosmic expansion and curvature of the universe, laying the foundation for modern cosmology. Einstein's theory revolutionized not only our conceptual framework, but also our practical understanding, influencing everything from GPS technology to the deepest questions about the origin and fate of the universe. Time dilation, a key concept derived from Einstein's theory of relativity, has profound practical implications for space travel. This phenomenon arises from the interaction of velocity and gravitational fields, leading to scenarios in which time can run at different speeds for observers in different states of motion or gravitational influence. In the context of space travel, especially at speeds approaching the speed of light, time dilation can create pronounced differences between the experiences of astronauts and those who remain on Earth. One important implication is the possibility that prolonged space travel could lead to age discrepancies between astronauts and people on Earth. For example, if astronauts traveled at close to the speed of light, they could return from a trip having aged only a few years, while on Earth decades or even centuries might have passed. This effect, known as Ndamp, the Twin-Ndamp, paradox, is not just theoretical. It has practical implications for planning future interstellar missions, affecting both the logistics and psychological aspects of deep space exploration. In addition to its theoretical implications, time dilation also affects current space travel technology. For example, accurate clock synchronization is critical to the operation of the Global Positioning System, GPS. Satellites in orbit experience both gravitational time dilation and velocity-related time dilation, causing their onboard atomic clocks to run at a slightly different rate than those on Earth. Engineers must take these differences into account to ensure the accuracy of position calculations and the day-to-day application of time dilation principles. In addition, understanding time dilation helps in developing strategies for human exploration of distant celestial bodies. Missions to planets such as Mars, which require significant flight times and exposure to various gravitational fields, require careful communication planning and coordination to account for relativistic effects of velocity and gravity. In the prospect of potential journeys to other star systems, relativistic effects become even more important, requiring advanced propulsion technologies and innovative solutions to take advantage of time dilation and mitigate its challenges. Time dilation is not just a fascinating theoretical idea, but a fundamental aspect of practical space travel that affects how we plan, execute, and conceptualize humanity's spacewalks. Gravitational waves, ripples in the fabric of spacetime predicted by Einstein's general theory of relativity, have opened an unprecedented window into space. These waves are generated by some of the most violent events in the universe, such as colliding black holes, merging neutron stars, or even the remnants of the Big Bang itself. When these massive objects accelerate, they distort space-time by sending out ripples that propagate at the speed of light. The detection of these waves provides insight into the structure of the universe and the fundamental forces at work in it. A major way in which gravitational waves deepen our understanding is their ability to convey information about cosmic events that are otherwise difficult or impossible to study. For example, when LIGO, the Laser Interferometer Gravitational Wave Observatory, made the first direct detection of gravitational waves in 2015, it observed the merger of two black holes. This event not only confirmed the existence of gravitational waves, but also provided the first direct evidence for the existence of binary black holes. Such mergers emit gravitational waves that carry unique signatures that allow scientists to determine the mass, distance, and rotation of the black holes involved in the merger. With continued observations, we can build a detailed catalog of black hole collisions, which will help us better understand their formation and evolution. Moreover, gravitational waves allow us to understand the extreme conditions and physics that occur when neutron stars merge. These cataclysmic events can produce kilowaves, emitting heavy elements such as gold and platinum, and allowing the study of nuclear physics under the most extreme conditions. The detection of gravitational waves from such events, combined with electromagnetic observations, creates a multi-messenger approach to astrophysics that provides a complete picture that can reveal the composition, structure, and behavior of neutron stars. Gravitational waves can also be used to study the early universe. Soon after the Big Bang, violent processes must have generated primordial gravitational waves, giving a direct indication of the infancy of the universe. If discovered, these primordial waves could provide empirical evidence for inflationary periods and fundamental particles, further illuminating the conditions that shaped the cosmos at its very beginning. Gravitational waves are a revolutionary tool in our quest to understand the universe. By allowing us to observe and analyze cosmic phenomena that would otherwise be hidden or opaque, they expand our knowledge of the structure, origin, and fundamental laws governing the cosmos. This emerging field promises to answer some of the deepest questions in astronomy and cosmology, combining observations with theory in new and enlightening ways. Wormholes, also known as Einstein-Rosen bridges, are theoretical passageways in space-time that can create shortcuts between distant regions of the universe. This concept emerged from Einstein's solution to the field equations in the general theory of relativity. Imagine space-time as a two-dimensional sheet. A wormhole is like folding a piece of paper so that two distant points touch each other, creating a straight path between them. The idea is appealing because it suggests the possibility of traveling at speeds faster than light, traversing the vast distances that currently limit human exploration of space. However, the existence of wormholes remains speculative. Although the general theory of relativity allows such structures to exist, they present several serious problems. First, for a wormhole to be passable, exotic matter, a material with negative energy density, would be required to keep the wormhole stable and open. The existence of exotic matter has not been confirmed, and creating or utilizing it, if possible, involves significant scientific and engineering challenges. Moreover, even if a stable wormhole could be created, the intense gravitational forces near the entrance could pose a serious danger to all potential travelers. Moreover, maintaining the stability of the wormhole from perturbations of particles and radiation passing through it is another major challenge. Calculations show that passable wormholes, if they exist, can be highly unstable and collapse rapidly in vivo. Practical considerations also include the energy requirements and technological advances needed to detect or create such cosmic phenomena, which are far beyond our current capabilities. Despite these difficulties, the study of wormholes continues to fascinate and stimulate research in theoretical physics. The concepts of quantum mechanics and the emerging field of quantum gravity may eventually provide new ideas or even technological avenues. Although wormholes currently belong to the realm of science fiction, they stimulate valuable discussions about the nature of space-time, the limits of human travel, and the fundamental laws governing our universe. Overall, while wormholes hold intriguing potential to revolutionize space travel, they remain a theoretical construct with numerous scientific and practical barriers that have yet to be overcome. Future discoveries in physics could either bring this concept closer to reality or open new ways to realize rapid space travel, continuing to fuel humanity's dreams of space exploration. Scientists study the curvature of space-time around massive objects using a combination of precise observations and sophisticated theoretical models based on the general theory of relativity. One basic method involves observing the effects of gravitational lensing. When light from a distant star or galaxy passes near a massive object, such as a black hole or a cluster of galaxies, the gravity of the massive object bends the path of the light. This curvature or lens can create multiple images of the same star, magnify a distant object, and even create arcs and rings of light. By analyzing these distortions, scientists can map the distribution and strength of the gravitational field, thereby drawing conclusions about the curvature of space-time in a particular region. Another method is to study the orbits of stars and planets around massive objects. For example, by tracking the orbits of stars near the supermassive black hole at the center of our galaxy, scientists can determine the mass of the black hole and the curvature of space-time around it. The most famous example is the orbit of the star S2 around the Milky Way's central black hole, the star Sagittarius A. The star's fast and curved trajectory indicates the presence of an intense gravitational field, which confirms the predictions of the general theory of relativity. More recently, the observation of a star's relativistic redshift as it approaches a black hole has provided more direct evidence of space-time curvature. Scientists also detect the curvature of space-time using gravitational waves, ripples created by massive accelerating objects such as merging black holes or neutron stars. Instruments such as LIGO and Virgo detect these waves, giving insight into the dynamics of the space around these cataclysmic objects. The resulting waveforms carry information about the mass and rotation of the bodies involved in the collision, as well as the nature of their collision, revealing the characteristics of space-time under extreme conditions. In addition, precise measurements of the orbits of satellites within our solar system by instruments such as Gravity Probe B have confirmed the presence of undamped frame dragging undamp and geodesic effects. Imperceptible shifts in the orientation of satellite gyroscopes caused by the mass and rotation of the Earth again confirm the predictions of the general theory of relativity. In all of these cases, the interplay between observational data and theoretical models allows scientists to deeply understand the curvature of space-time around massive objects. This not only confirms Einstein's theories, but also deepens our understanding of fundamental properties of the universe, from the behavior of black holes to the dynamics of galaxy clusters, and potential insights into new physics beyond our current models. Space-time singularities, mysterious points where gravitational forces become infinite and the known laws of physics cease to apply, are surrounded by deep mysteries that challenge our understanding of the universe. The best-known examples of singularities are found at the centers of black holes and at the very beginning of the universe, similar to the Big Bang. These regions are characterized by space-time densities and curvatures that are so extreme that standard notions of space and time are shattered. One of the most puzzling aspects of singularities is their very existence in solutions to the equations of Einstein's general theory of relativity. These equations predict that under certain conditions, such as the collapse of a massive star, the gravitational field can become so strong that space-time is curved infinitely. However, this prediction leads to the destruction of determinism, where the future and past states of physical processes can no longer be accurately predicted. The naked singularity and scenario contradicts the cosmic censorship hypothesis proposed by physicist Roger Penrose, according to which singularities must always be hidden in event horizons beyond which they cannot affect the observable universe. Another important mystery associated with singularities is the interaction between general relativity and quantum mechanics. General relativity theory successfully describes the macroscopic world of stars, galaxies, and the cosmos as a whole, while quantum mechanics does an excellent job of explaining microscopic phenomena such as particle interactions. However, these two pillars of modern physics are fundamentally incompatible in situations involving extreme gravitational fields and very small scales, such as singularities. A fully developed theory of quantum gravity that seamlessly integrates these two systems is necessary to resolve the paradoxes associated with singularities. Hypotheses such as string theory and loop quantum gravity have sought to address these questions, but a definitive solution remains elusive. These mysteries are exacerbated by an information paradox that is particularly significant for black hole singularities. According to the classical general theory of relativity, any information that enters a black hole is lost to the external universe and is only preserved in the singularity. However, quantum mechanics states that information cannot be annihilated. Reconciling these conflicting views challenges existing theories and leads to various speculative ideas, such as the holographic principle, which suggests that information in a volume of space can be thought of as encoded at the boundary of that space. Finally, the Big Bang singularity presents its own set of questions. As the universe approaches the initial singularity, it becomes incredibly hot and dense, and classical explanations collapse. What existed before the Big Bang and what caused it are deep mysteries that are currently beyond the control of observational science, and they are deeply intertwined with the search for a unified theory. Singularities are thus at the frontier of physics, representing both the limits of our current theories and the tantalizing promise of deeper understanding. These cosmic mysteries force us to push the boundaries of cognition, stimulating ongoing attempts to develop a more complete and unified description of the universe. Particle gas pedals are sophisticated tools that allow us to understand the fundamental nature of matter and space-time. By accelerating particles to nearly the speed of light and colliding them, these machines recreate conditions similar to those just after the Big Bang, allowing scientists to explore the fundamental forces in particles that make up the universe. One of the most famous examples is the Large Hadron Collider, LHC, operating at CERN, which accelerates protons and heavy ions to enormous energies and then collides them with each other. High-energy collisions produce many particles, some of which exist only fleetingly under ordinary conditions. By studying these particles and their interactions, scientists can test and refine the standard model of particle physics, the theory that describes the electromagnetic, weak and strong nuclear interactions. The discovery of the Higgs boson at the LHC in 2012 confirmed one of the most important aspects of this model, clarifying how particles acquire mass through the Higgs mechanism. This breakthrough has impacted our understanding of space-time by providing insight into the field that permeates the universe and influences the structure of the cosmos itself. In addition, particle-gas pedal experiments investigate phenomena that may provide clues to the nature of space-time on extremely small scales. For example, studying proton-proton collisions at very high energies could potentially reveal deviations from the standard model, hinting at new physics such as supersymmetry or extra dimensions. Theories beyond the standard model, including string theory, suggest that space-time may have more than just the familiar 4 dimensions, 3 spatial and 1 temporal. High-energy collisions can produce particles or effects that indicate the existence of these extra dimensions, which has direct implications for our understanding of the underlying structure of the universe. Particle gas pedals also explore the properties of quark-gluon plasma, a state of matter thought to have existed microseconds after the Big Bang. Heavy ion collisions allow physicists to recreate and study this plasma, which provides valuable insights into the behavior of strong nuclear forces at extremely high temperatures and densities. Understanding these forces and states of matter helps piece together the early evolution of the universe, giving a clearer picture of how space-time and fundamental forces evolved. In addition, particle gas pedals make it possible to simulate the conditions under which the principles of quantum field theory and general relativity are tested. For example, predictions about how particles should behave in strong gravitational fields can be compared to observed behavior in high-energy collisions, offering an indirect test of the mutual consistency of these theories. This is fundamental to advancing toward a theory of quantum gravity, a goal that seeks to unify general relativity and quantum mechanics. Particle gas pedals serve as both microscopes and time machines, allowing us to explore the deepest layers of reality and the earliest moments of the universe. Through these experiments, scientists are not only confirming existing theories, but also discovering new phenomena, pushing the boundaries of our knowledge of space-time and the myriad forces that shape the cosmos. The theoretical implications of FTL travel are profound and far-reaching, touching the very foundations of physics and our understanding of the universe. According to Einstein's special theory of relativity, when an object approaches the speed of light, its mass effectively becomes infinite, and the energy required to accelerate it further grows without limit. It follows that FTL travel, at least as conventionally understood, is fundamentally impossible. However, speculative concepts explore the implications and theoretical underpinnings that could enable FTL travel. One of the most famous hypothetical designs is the concept of a warp drive, inspired by a 1994 proposal by Miguel Alcubierre. Alcubierre's model suggests that it is possible to compress space-time in front of a spacecraft and expand it behind, allowing the craft to traverse space-time waves, thus traveling faster than light relative to outer space, but not locally breaking the light speed barrier. At the same time, relativity is preserved because the spacecraft itself is not traveling faster than light in its local space-time bubble. However, it requires exotic matter with negative energy density, the existence of which has not been proven, and its use is not possible. Another speculative avenue involves wormholes or Einstein-Rosen bridges. If these hypothetical structures could be stabilized, they could serve as shortcuts through space-time, potentially allowing instantaneous travel between distant points. However, the stability and creation of passable wormholes would require exotic conditions of matter and energy that are currently beyond our technological and theoretical capabilities. The theoretical implications of such FTL mechanisms, if they could exist, are astounding. FTL travel would defy cause and effect. the principle that what causes happens first. The theory of relativity suggests that FTL travel could lead to situations where effects can occur before causes, potentially leading to paradoxes such as traveling back in time. This raises difficult questions about the nature of time and reality itself, requiring new physics or revised interpretations of existing theories. Furthermore, the existence of travel at faster than the speed of light would revolutionize our understanding of distances and connections in space. Interstellar and even intergalactic travel could become conceivable, fundamentally altering our view of the size of the universe and our place in it. Such possibilities will have profound implications for the search for extraterrestrial life, the colonization of other planetary systems, and the ultimate future of humanity. Interestingly, some recent theoretical advances in quantum mechanics suggest phenomena that may mimic some features of superluminal communications, such as entanglement, where particles act in interconnection instantaneously over vast distances. However, these "spooky actions at a distance," as Einstein called them, do not actually transmit information faster than light, and thus do not violate relativity. In sum, while the concept of FTL travel remains in the realm of theoretical speculation and science fiction, its implications are deeply intertwined with the fundamentals of physics. Exploring these ideas, whether through warp drives, wormholes, or quantum phenomena, forces us to rethink the nature of space, time, and the universe itself. Such research is pushing the boundaries of current scientific knowledge, potentially leading to revolutionary breakthroughs or a profound new understanding of the cosmos. String theory, the main contender for a unified theory of quantum gravity, is an exciting reconfiguration of the traditional concept of spacetime. At its core, string theory posits that the fundamental entities in the universe are not point particles, as traditionally believed in particle physics, but one-dimensional strings that can oscillate in different modes. The vibrations of these strings correspond to different particles, where each mode of vibration represents a different kind of particle. The move to one-dimensional strings has profound implications for our understanding of spacetime. First, string theory requires additional dimensions beyond the usual 3 dimensions of space and 1 dimension of time. Although the exact number of dimensions can vary depending on the particular formulation of string theory, the most commonly studied versions assume 10 or even 11 dimensions. These extra dimensions cannot be observed directly because they are thought to be compressed or folded on such a small scale that they are effectively hidden from current experiments. The existence of extra dimensions offers potential solutions to a number of physical problems. For example, it provides a framework for unifying all fundamental forces, including gravity, in a single theoretical architecture. The traditional general theory of relativity does not treat gravity as a curvature of 4-dimensional space-time caused by mass and energy. In string theory, gravity is still a manifestation of space-time geometry, but now in the context of a higher dimension. This higher dimensional space-time can manifest itself in many different forms, leading to different physical laws in contexts of different dimensions. In addition, the higher dimensionality of string theory allows us to resolve conflicts between general relativity and quantum mechanics. In the classical 4-dimensional framework, singularities, such as in black holes or the Big Bang, can lead to infinity, which violates physical laws. The extended structure of string theory, through mechanisms such as string interactions and the inclusion of extra dimensions, can smooth out these singularities, potentially avoiding meaningless infinities and providing a more consistent quantum theory of gravity. One of the most intriguing aspects of the space-time implications of string theory has to do with D-branes, the multidimensional objects of the theory to which strings can attach their endpoints. These branes introduce new dynamics and lead to scenarios in which our universe may be a 4-dimensional slice within a higher dimensional space. This scenario, often referred to as the brain-world hypothesis, opens the door for phenomena such as gravity leaking into extra dimensions, offering a potential explanation for the relative weakness of gravity compared to other fundamental forces. In addition, string theory revives the idea of dualities, connections that indicate that seemingly different physical scenarios are actually equivalent when properly considered. These dualities could link different types of string theories or even connect higher and lower dimensional theories, suggesting that space and time may be emergent properties rather than fundamental constructs. This concept further changes our understanding of the very fabric of reality. String theory revolutionizes the concept of space-time by introducing additional dimensions, proposing new fundamental entities, and offering a unified structure that reconciles gravity with quantum mechanics. These innovations not only challenge traditional notions, but also provide fertile ground for solving some of physics' deepest mysteries, potentially leading to a deeper and more comprehensive understanding of the universe. In the field of relativity theory, one of the deepest and most perplexing questions still unanswered is the harmonization of general relativity theory with quantum mechanics. The general theory of relativity, formulated by Albert Einstein, perfectly describes gravity as a curvature of space-time itself, affecting large and small masses. On the other hand, quantum mechanics governs the microscopic world with remarkable precision, explaining the behavior of particles at the smallest scales. However, these two systems operate on fundamentally different principles that are not easily synthesized. The task of unifying these two giants into a coherent theory of quantum gravity is an enigma that has puzzled physicists for decades. This quest is opening up deeper layers of reality, perhaps revealing the nature of black holes, the origin of the universe, and the structure of space-time at the Planck scale, a mind-bogglingly tiny scale where classical and quantum effects are thought to merge. Another tantalizing mystery in the study of relativity is the true nature of dark energy and dark matter. Observations have shown that ordinary matter, of which stars, planets, and all visible structures are composed, accounts for only about 5% of the total energy content of the universe. A staggering 70% is attributed to dark energy, the unknown force causing the accelerated expansion of the universe, while dark matter accounts for about 25%, influencing the formation and clustering of galaxies through its gravitational influence. Despite knowing their significant role, scientists are still in the dark, literally, about the composition and mechanisms of these invisible entities. Understanding dark energy and dark matter could fundamentally change our understanding of not only the theory of relativity, but also the fundamental structure of the universe, painting a more complete picture of the past, present, and future of the universe.